Hello my dear student friends, welcome you all to this video lecture series of network analysis. In previous lecture we had a discussion about how to derive the equation of modified network M-derived filters, right? So for T and pi sections we have derived the Z1 dash and Z2 dash, right? So in case of T network we have found out what is the changes into the Z2 dash, right? And in case of pi network we have found out Z1 dash. Okay, so remember that in case of pi and T network, okay, so the changes into the series, and this is nothing but your shunt arm and this is nothing but your series arm. Okay, so these impedances have been changed. Okay, so shunt and series arms of your regular or prototype T and pi networks have been changed, right? And over here it is a series combination of two impedances, and in this case of pi network it is nothing but a parallel combination of these two impedances, right? But in case of whenever you are going to design the filters, then it these two components are nothing but L and C, and it is forming the resonance circuit. Okay, so these are two forming the resonance circuit, and we know that the condition of resonance, right? So at resonance the impedances of capacitor and inductor, they are going to become equal, right? This you know very well. Okay, so we have already studied what is resonance and all these things. I am not going to repeat it, but we know the condition of resonance is what? At resonance the impedances of capacitive and inductive reactances are going to become equal, right? So over here the same thing is going to occur. So for T network the shunt arm is to be chosen such that it is resonant at some frequency f alpha. Okay, so we are going to select the shunt arm of T network, right? So this is nothing but the shunt arm of a T network, right? And this we are going to choose in such a way that it will resonate at some frequency, that is f alpha, and which is greater than cutoff frequency of this filter. Okay, so suppose this is a low pass filter or high pass filter. Based on that we are going to select the f alpha, which must be greater than cutoff frequency. Are you getting it? Okay, and in case of pi network this also is going to satisfy the criteria of resonance, and this will also resonate at frequency f alpha, which is also greater than your cutoff frequency of that particular filter. Is that fine? Okay, so if the shunt arm is a series resonance, its impedances will be minimum or zero. Therefore, output is zero and will correspond to infinite attenuation. So once we are going to select the shunt arms of the series resonance, then the impedances will be minimum or zero, right? Because as these two reactances are going to become equal and they are opposite in magnitude, so once we are going to become these two impedances equal, then once their subtraction is going to result as definitely zero, or it will be minimum, right? So once it is minimum, that means this arm is as good as it is short circuited, right? So it will have a minimum resistance path, so whatever the signal is going to pass through it, it is going to get directly grounded. So this is nothing but your ground connection. So in case of low pass filtering, all the frequencies above the cutoff frequency, they will get attenuated and they will transfer to the ground. So that's why all the frequencies above cutoff frequency, okay, all the frequencies, let us say f above cutoff frequencies, they are going to become attenuated, or they are simply having the value as 0. Are you getting it? So that is the use of resonance again in case of filtering. So remember that resonance is a very important phenomenon as far as your electronics and telecommunication engineering is concerned. Okay, so same thing is going to occur in this case also for the pi network. So this is nothing but a parallel resonance, and this is nothing but your series resonance, which is present in the shunt arm. Okay, this is nothing but connected in parallel to this series inductors, right? ML by 2 and NL by 2. So this is nothing but the shunt arm of this network, but this is nothing but a series resonance type of network. Okay, RLC circuit we have seen, right? And this is nothing but LNC which are connected in parallel, and because of that the resonance is going to occur. Okay, so remember this one. Okay, so we know the condition at resonance. At resonance, XL and XC are equal, right? So that's why the shunt arm of T network, so this is nothing but the shunt arm of a T network, it is going to have the XL is equals to XC, because this must have a resonating circuit, right? So because of that the resonance condition is nothing but XL is equals to XC. So what is XC? XC is nothing but 1 upon omega C. But what is C? C is nothing but M into C. So therefore 1 upon omega M into C will be there. Okay, is equals to omega R. What is L? L is nothing but 1 minus M square divided by 4M into L, right? So the same thing we are taking over here, right? Okay, so therefore omega R into 1 minus M square divided by 4M into L, right? Suppose for example, if 2C is there, right? So how we are going to write capacitive reactance for that? XC is nothing but omega into 2C. Are you getting this? Okay, so in the similar case, how we are going to write omega L for 2L? It is nothing but XL is nothing but omega R into 2L. Are you getting this? So this is very basic fundamental related to it, right? So the same thing we have done, right? So M is nothing but, for example, it is 2, for example, okay, and this is nothing but, let us say again a 2. Then it is simply multiplied with L. This is simply multiplied with C, but into the denominator for XC and into the numerator for XL, because their equations are like those. Okay, great. So from that we are interested to find out what is the equation for M. So that is our main intention for doing all these things. Okay, so we must know, or we must get some equation so that we can find out what is the modification factor which is required to have the different design of filtering. Okay, so we can design the different filter with, that is nothing but your modified filter, but for that we must know what is the modification factor equation. Okay, so for this we are doing this. Okay, so let us take omega r square on one side and let us take all the terms related to M on the one side. Okay, so we have done this. Okay, so omega r we have transferred on this side. Now all the values we have transferred up to at this point. Okay, so this is nothing but representing 4M, right? So once I am going to transfer it to the left hand side, this is going to become into the numerator, right? This L will be into the denominator. This 1 minus M square will be also into the denominator, right? So 1 minus M square, this MC will be as it is, MC, and this L, right? And that is equals to omega r square. We have transferred this omega r square, omega r to the left right hand side. So it is going to become omega r into omega r as M square. So this M and this M is going to get cancelled out, right? So 4 divided by 1 minus M square LC is equals to omega r square. Now what is omega r? Omega r is nothing but 2 pi fr, right? Yes. So 4 divided by 1 minus M square LC is equals to omega r is nothing but 2 pi fr, it's a square, right? Okay, now let us go to the next page. I hope you understood everything, right? Okay, we have came up to this point, right? So 2 pi fr bracket square that we are going to expand, we are going to give the separate square. So 2 pi square fr square is equals to 4 divided by 1 minus m square L into c is nothing but this equation. So we can cancel out now 4, this 4. Okay, now let us find out fr square is equals to 1 upon 1 minus m square under root, sorry, pi square LC, right? Let us take the square root of this. Okay, so that fr is nothing but 1 upon 1 minus, okay, before that, fine, let it be under root of 1 minus m square into pi into root LC. So what is this? This is 1 upon pi root LC is nothing but the cutoff frequency equation of constant K low pass filter, right? So this is nothing but the equation of constant K low pass filter cutoff frequency, right? So instead of writing this 1 upon pi root LC, we are going to write now FC. Is that fine? And we did the same over here into the next step. Okay. So this we have replaced by FC. So FR is equals to FC divided by 1 minus m square. Now let us find out the relation of m, right? So for that purpose we need to go for again squaring on both sides so that we can simplify this, and ultimately we can find out the relation of or equation of m. Is that fine? Okay, so we have made square on both sides. Okay, we have transferred this term to the left hand side and we have taken the fr to the right hand side. So squaring on both sides, 1 minus m square is equals to fc square divided by fr square. Now let us transfer this term to the left hand side and let us take this m to the right hand side. So m square is equals to 1 minus fc square divided by fr square, and let us find out then m. So m is nothing but it's under root of 1 minus cutoff frequency square divided by fr square. Sometimes you may find fr is equals to f infinity, or this is called as infinite attenuation frequency, right? Infinite, sorry, attenuation frequency. Is that fine? So sometimes this fr will be denoted as f alpha, f infinity also, right? Remember this one. Okay, it is also written as f infinity sometimes, f alpha sometimes, right? So you must not get confused what is that f infinity, what is that f alpha. Okay, all these are nothing but your resonant frequencies, or they are also called as infinite attenuation, because lot of infinite attenuation is going to occur after this cutoff frequency for this modified filter designs. Are you getting it? Great. So this is nothing but the derivations. Now we are going to have the design problem based on this. Okay, so let us go for the constant K low pass filter first, and then we'll go for constant K high pass filter. Are you getting it? Great. So the question is, design a M-derived low pass filter having the cutoff frequency of 1 kilohertz, then design impedance, that is nothing but your K, is of 400 ohm, and the frequency of resonant, that is nothing but this is nothing but your resonant frequency FR. Okay, so the given parameters are nothing but what? 1 kilohertz is the cutoff frequency of the particular filter, then the design impedance is nothing but 400 ohm. Remember that the formulae, whatever you are going to use for low pass filter is nothing but as that of your constant K low pass filter, because this M derived filter is derived from the constant K filter. So whatever the formulae for inductor and capacitor that we have used for constant K low pass filter, the same formulae we are going to use for inductor and capacitor. Okay, only the change is what? Its modification factor is going to change, so that we are going to compute, and with respect to that we are going to compute the values of the series and shunt arm impedances. Are you getting it? So series and shunt arm inductor value and capacitor value will get modified because of this modification factor. Are you getting it? Okay. So remember that the things must be clear. We are going to use the same formulae of low pass as well as high pass for M-derived low pass filter and uh, M-derived high pass filters as like that whatever we have derived for constant K low pass and high pass filters. Okay, so inductor and capacitor formulas will remain same, only the modification factor is going to have the different value, and because of this different value the values of the inductor and capacitors into the particular M derived circuit, that is T and pi network, they are going to change. I hope you are getting the things. Okay, so from this circuit now you can identify because of this M, this L value is going to change, because of this M it is going to change, because of this M, because of this value it is going to change the value of inductor. So remember this one. I hope the things are clear to you people. Okay, so let us design the problem. Great. So first thing is what? You have to first find out the value of M, modification factor. How to find out? The formula for that is nothing but under root of 1 minus Fc divided by Fr bracket square. What is Fc? Cutoff frequency is 1 kilohertz. Fr is nothing but 1.1 kilohertz. So after calculating that, we have got M as 0.4165. Okay. So this is your modification factor that you are going to multiply for capacitor and inductor in order to find out the new values of inductor and capacitor. Is that fine? Okay. So once we have found out M value, then the thing is that we need to find out the capacitor and inductor. Okay. So the same formula we have used for this also as that of your constant K low pass filter. Okay. Okay, so C is nothing but 1 upon pi FCK, right? And from that, once I am going to put the values of cutoff frequency and design impedance, then I will be getting the value of capacitor as 0.79 microfarads, and the formula that we have used for inductor is nothing but again the same formula from your constant K low pass filter. So it is nothing but K divided by pi FC, right? So it is nothing but K divided by pi Fc. Once I am going to put the value, I will be getting the value of inductor as 0.127 henries. Okay, fine. Now the main task begins over here. Once we have calculated all the values of your M, L and C, now we have to find out the value of ML by 2, then that C into M, right? Then 1 minus M square divided by 4M into L, right? So these are the values that we need to find out the corresponding component values of L and C for the T network as well as for pi networks, right? So I hope you still remember that the series arm is consisting of ML by 2, right? This is also ML by 2. This is nothing but a capacitor. Capacitor is having M into C. Then the inductor is having the value as 1 minus M square divided by 4M into L. So this, now we have to perform the calculations. So we need to find out what is the value of this with respect to M and L. We have to find out the value of this component, that is capacitor, with respect to modification factor, and we have to find out the value of this inductor with respect to this particular formula. So let us find it out. ML divided by 2, once I am going to put the value of M, L, whatever we have computed over here, then I can get the value of new ML by 2 is nothing but 0.026 Henry. So this value will be represented over here as well as represented over here, right? Okay, then let us compute the value of M into C. M is nothing but 0.416 and the capacitor value is nothing but 0.79 microfarad. Once I am going to perform the operation or computation, I will be getting this value as 0.33. Okay, so like that we are going to write the values of these components at appropriate positions, and finally let us compute this one. Okay, so 1 minus m square into L divided by 4 into m, right? So once I am going to compute this, I will be getting 0.063 henries. Okay, so once we are computing, we have computed all the values for the T network. We are going to draw the network and we are going to write their corresponding values. Okay, so ml by 2 we have written over here. Okay, so same thing we have written over here. Then this is nothing but your m into c that we have written. This 1 minus m square divided by 4m into L, this we have computed and we have written the corresponding values over there. I hope the thing is very clear to you people. Fine. Now let us go for pi network. Okay, so for pi network, what is the thing? The thing is what? The series arm is nothing but consisting of a parallel combination of inductor and capacitor, and this is nothing but your inductor. Sorry, capacitor, not inductor. This is also capacitor. Sorry, yes. For T network, it is yes. It is MC by 2, right? It is capacitor. Okay. So remember that we are designing low pass filter. So for low pass filter, capacitor must be in shunt only. Okay. Now this is nothing but what? 1 minus m square divided by 4m into c, right? This is nothing but ml. This is nothing but what? cm by 2, right? So let us compute this. Cm by 2 is nothing but 0.416 into c divided by 2. Once we are going to compute this, that we are going to write it for this value. Okay, or for at this place we are going to write the particular value. Then let us compute this and then we are going to write it over here, right? So 1 minus m square divided by 4m into c is equals to, once I am going to compute this one, I will be getting 0.395 microfarads, and that will be written over here. Then lastly we are going to find out ml. M into L is nothing but 0.0258 henries, and that we are going to write it at this position. So let us draw the circuit diagram. Okay, I hope you got this. Is it fine? So once we are going to compute all the values, we are going to write those values at appropriate places. Once you are going to write it and draw it properly, then only you will be getting 8 marks fully. Okay, if you are going to find out only the values of inductor and capacitors, then you will be getting a half mark. The half, that means 4 marks you will be getting, and 2 marks are for this one up to this circuit diagram, and 2 marks for this calculation and to this circuit diagram. I hope the thing is clear to you people. Okay, now let us go for one more example. You just write this problem, okay, and you only solve this and forward it to me as an assignment. Okay, I hope you can write it down. Okay, so design a T section as well as a pi section of a M-derived low pass filter having cutoff frequency 3 kHz and a resonant frequency 3.2 kHz, having a design impedance of 600 ohm. So this is the problem for you for 8 marks. Okay, if it may be asked for your examination. So remember that this question was asked in May 2009 in case of your university, Shivaji University syllabus. Okay, so you have to solve this. Is that fine? Now let us go for M-derived high pass filter. Okay, so remember that wherever there is a capacitor, we are going to replace it by inductor, and wherever there is a inductor, we are going to replace it by capacitor, right? So inductor is replaced by capacitor and capacitor is replaced by inductor, vice versa, right? So in previous case, in case of low pass filter, it was having an inductor over here, but right now we have changed it to capacitor, and because of that 2C divided by M, 2C divided by M is over here. In spite of writing over here, it was consisting of your inductor, no? Previously 1 minus M square divided by 4M into L was there. Now over here it is C, so it is getting inverted, right? So 4M divided by 1 minus M square into C, then it is L by M, right? Okay. And similarly, this is nothing but your 4ml divided by 1 minus M square. This is nothing but C by M. This is 2L by M, 2L by M, right? Great. So this is nothing but M-derived high pass filter. Okay. Again, the same thing is there. This series arm must be a resonating circuit, and this shunt arm must be a resonating circuit, right? So these are must be a resonant creating circuit. So this is series resonance, this is parallel resonance, right? Okay, so same thing is there also. Okay, again, if the shunt arm in T section is series resonance, it must offer minimum resistance or zero impedance, and because of that the output is zero, and thus at resonance frequency or frequency corresponding to the infinite attenuation, the condition for that is nothing but, that is the resonance condition is nothing but what? XL is equals to XC. So what is XL? XL is nothing but omega L divided by M. So just check it out, the series arm of your T network. What is XL? XL is nothing but omega L divided by M, right? So as it is divided by M, it will be simply as it is. Okay, that means if L by 2 is there, then XL must be what? Omega L divided by 2, right? So like that. And if their capacitor is there, then it is going to get inverted. So let us check it out. So 1 divided by omega into C is what? 4m into C divided by 1 minus M square. Now this 1 minus M square will appear into the numerator. That will check it now. Okay. So let us take the omega r on the one side. So this is nothing but your omega r. So omega r will taking at the one side, right? And this is nothing but your omega r square is equals to 1 minus M square divided by 4 LC, because this M and this M is going to get cancelled out, and this 1 minus M square we have taken at the numerator side, right? Okay. So therefore this is nothing but the simplified step 1 minus M square divided by 4 LC, right? Now let us square on both sides. Okay. So 4 pi square fr square is equals to 1 minus M square divided by 4 LC, it is there. So fr square, let us find it out. 1 minus M square divided by 4 into 4 is nothing but 16 pi square LC, right? Okay. What is this? So remember that cutoff frequency of constant K high pass filter is 1 fc square is equals to 1 upon 16 pi square LC, or you can write fc is equals to 1 upon 4 pi root LC. It is the cutoff frequency of constant K high pass filter. So can I write it cutoff frequency of high pass filter? Yes, definitely I can write it. So fr square is equals to 1 minus M squared into fc square. Yes, right. So now let us find out M for this as well. Okay, so for that we are going to performing this. Okay, so this is nothing but we have done already this one. Yes, so over here fr square divided by fc square is equals to 1 minus M square, right? Because fr square is equals to 1 minus M square into fc square was the equation, and therefore you have taken that fc square at the one side, right? 1 minus M square. Now let us find out. Let us take this term to the left hand side and let us transfer this m square on the other side. So m square is equals to 1 minus fr square, or we can write the square as a common as a bracket, and then finally m is nothing but under root of this. So in case of your low pass filter, this ratio was different. It was fc divided by fr, right? And over here, in case of your high pass filter, it is simply inverted. So you just remember that. You can remember the m formula for low pass filter. That's it. And you have to remember that. How you are going to remember it? The formula for high pass filter, M-derived high pass filter, M formula for the high pass filter is nothing but what? Only the FC and FR positions have been inverted, right? So that is nothing but a reciprocal of the same what we can call frequencies, reciprocal of those frequencies you have to take, okay? And that's it. So you don't need to remember the formulas, okay? So I have given you the different techniques to remember the formulae. If you are going to mug up these all the formulas, then you may mess up with this, okay? So don't mess up with this. You just need to remember that. How you are going to remember? First you need to remember the constant K low pass filter formula. What is that? For L, it is nothing but what? K divided by pi Fc, right? And for capacitor, it is nothing but 1 divided by pi K Fc, right? If you remember these two formulae, then high pass filter can be written, constant K high pass filter can be written as L is equals to K divided by only 4 is extra into the denominator. Yes, and that is also a case, same case in case of capacitor as well, right? Understood? Okay, I hope I have written the correct formula. Let me check it once again. Yes, I have written it correctly. Yes, C is nothing but 1 upon pi Fc K. Yes, and L is nothing but K divided by pi Fc, right? Okay, so once you remember these two formulae, now what is next? You can derive easily a high pass filter, right? Now how to remember M? M is nothing but for low pass filter, M derived low pass filter. What is the formula for M? 1 minus cutoff frequency first and then resonant frequency. It's a square, and M for HPF is nothing but what? This terms reciprocal, you have to write it. That's it. So M is equals to 1 minus FR divided by FC, and it's a square. That's it. So this step or this particular slide will give you all the details of your constant K filter, high pass filter, low pass filter, then M derived low pass filter, M derived high pass filter. Only the thing is that you have to remember the positions and particular equations of ml divided by m into L divided by something, right? So that you need to remember. Okay, that means ml by 2. Okay, so c divided by 2 m, like that. Okay, so 2c divided by m, like this. You need to remember 1 minus m square divided by 4m into L. These positions you must remember. Okay, so you have to make a practice of this. Okay, okay, now let us go for designing this M-derived high pass filter. Okay, so let us design the M-derived high pass filter. Design M-derived high pass filter with a cutoff frequency of 10K, design impedance of 500 ohms, and they have directly given you M. Okay, so no need to calculate M. Once you are going to calculate the capacitor and inductor, then you directly go to calculate the corresponding values of capacitor and inductor with respect to modification factor M, which they have given into the problem itself, right? Okay, so let us design this problem. So the given parameters are nothing but cutoff frequency. They have given you 0.5, sorry, m is equals to 0.4. Okay, then k is 500. Okay, so once we got this, so the requirement for our calculation of capacitor and inductor is what? Only cutoff frequency and k, that we need. Okay, so as I discussed just before this, so this is nothing but the formula for capacitor is nothing but 4 is extra into the denominator, right? Okay, so once you are going to write it, put the values of k and c. K is nothing but 500, c is nothing but, that is fc is nothing but 10k. So once we are going to compute this, I will be getting capacitor as 0.0159 microfarad and inductor as 0.3978 millihenries, right? So these are the values of inductor and capacitors. Now let us compute for T and pi networks. Okay, so these are the corresponding equations or values of T network. So over here we are going to design the T network, right? So 2c divided by m, we are going to find it out first, and that is coming as 0.0795 microfarads. This we are going to write it at this place and at this place. Now let us compute this. Okay, 4m divided by 1 minus m square into c. So once I am going to compute it, it is going to come as 0.0302 microfarads, and I am going to write it at this place. And then finally L divided by m, and that is coming as 9.92 millihenry. I can write it over here. Now let us go for pi network. This was your T network. Okay, so for pi network, this thing, yes, C divided by m is nothing but 0.0397 microfarad. We are going to write it at this place. Then let us compute 2L divided by m, that is nothing but this one. So once I am going to compute it, it is coming as 0.198 henries. You can convert it in millihenry also, no problem at all. Then lastly, let us compute this one. This value you are going to write it at this both places, right? So let us compute last one, and that is coming as 7.56 millihenry, right? And that we are going to write at this place. That's it. So likewise, once you are going to find out all the values, you need to write those values at the corresponding places. Okay, so once you are going to write those values at the corresponding places, you will be getting 8 marks. Okay, so this is another problem that you can solve it as an assignment. Okay, so you just write it down. Design T section of an M-derived high pass filter having the cutoff frequency as 3000 Hz and f infinity. Now just remember that f infinity is nothing but your resonant frequency, and that is nothing but 2700 Hz, and sometimes it may be represented as R0. R0 is nothing but your design impedance or nominal impedance, okay, or characteristic impedance, right? So that is nothing but your K actually. Got it? Okay, so this is nothing but your K. This is your FR. Okay, and you know this, it is cutoff frequency. Okay, so solve this and send it as an assignment. Okay. Okay, so now the next point is nothing but band pass filter. Okay, so constant K band pass filter. This is a constant K band pass filter. Okay, this I think we will discuss in the next session. Okay,